LC circuits. An LC circuit always has which two circuit elements present? Well, the L indicates that we have an inductor, and the C indicates that we have a capacitor. So that's an LC circuit. We're going to assume that the resistance of our circuits is 0. That'll keep things relatively easy. The figure shows a circuit with a capacitor C, a battery E, and an inductor L. The capacitor is initially uncharged. The following scenario begins when the switch is thrown to 0.1. We're going to do a lot of circling. We're going to throw this switch right there to 0.1. So that connection is made. In the bottom half of the circuit, current will flow in which direction? I'm looking at the battery now. The bottom half of the circuit, it's going to flow clockwise. Given that there are no resistors in the bottom part of the circuit, for how long will the current referenced in part C continue flowing? You can see that there's a capacitor there, so just an instant. You want to charge up a capacitor in a hurry, just hook it up to a battery. So just for an instant, current's going to flow and then it's going to stop. At this point, which plate will have the higher potential? So remember, we have flipped the switch to 0.1 here, and current has flowed in this direction, and so the higher potential will be plate percentage here, and that will be the positively charged plate. I could put some plus signs there. I'll just put 1 and some minus signs there. Higher potential on percentage plate. I've just labeled them percentage plate because I didn't want to label them L and R because left and right, because L is an inductor and R is a resistor, and that would just make things even more complicated. So I've labeled them as such. Now the switch is thrown to 0.2. So remember, this is a positively charged plate. This is a negatively charged plate. Now we're going to flip the switch here to 0.2. What's the initial current that subsequently flows in the top half of the circuit? Well, now we're taking into account the inductor. The inductor has had no current going through it. And now when we flip the switch up here, now there's the potential for current to be flowing through that. But remember, inductors don't like change. And so for that first instant, they are successfully able to resist any change in that current. So there will be 0 current flowing there at that first instant. When it does begin to flow, it's going to flow away from the positive plate and toward the negative plate. I think it's going to flow clockwise. In the top here, the current is going to build. And how does it do that? We flip the switch to 0.2. Increasing linearly? No. Increasing rapidly at first and then tapering off. There you go. Up to this point in the process, the inductor has had an induced EMF that points which way? Well, it's been fighting the push of the capacitor. It's going to be directed to the left in that direction. Up until now, the magnitude of the inductor's EMF has been, it was a maximum at first, wasn't it? So any of this increasing stuff is definitely no good. Decreasing linearly, that's never a good choice. Decreasing rapidly at first and then tapering off, or decreasing slowly at first and then at a greater rate. There's always a lot of change right at first, and then the rate of change tapers off. Once again, we are at a point where we have flipped the switch to number 2 here, just after the current reaches a maximum. So we have current now that has been building in the clockwise direction around this top part of the loop. It will reach a maximum. And right after that maximum, then the capacitor is going to be unable to push more current. And so now that current is going to try and drop off. Well, remember, inductors, they're kind of like cats, you know? They want to go outside, so you open the door and they walk out, and then you look out the door, and then they're looking at you again like, I want to come in. And so you say, oh, okay. So you open the door and they come in, and then they look at the door like they want to go out. It's like, dude, make up your mind. Inductors are like that. They've been fighting the buildup of current this whole time. But now, when the capacitor plates, at that instant, they'll be uncharged. As soon as that current tries to taper off, now the inductor says, hey, I want that current like I had it before. Inductors are kind of finicky. In the following moments, what's going to happen to the magnitude of the inductor's EMF? It's not going to be increasing, and it's not going to decrease linearly. It's going to decrease rapidly at first and then taper off. And that EMF is going to continue to push current in the clockwise direction until the $ plate is positively charged. So that one's going to be positively charged, and that one's going to be negatively charged. Now what happens? When we left off, the switch had been thrown to point 2, and we had reached the point at which the current had momentarily ceased flowing in the top half of the circuit, and we now continue. We flip the switch here. That plate we said was positively charged now, and that one's negatively charged. Now what's going to happen? Current is going to attempt to flow counterclockwise. And which way is the inductor's EMF going to point? Remember, for an instant there was 0 current. And now there's going to try to be current going to the left through the inductor. And remember, inductors, they just don't like change. So when it hits 0, and then we start to try to move current through it to the left, the inductor is going to fight us. For this part, when current resumes in the top, which way is the inductor's induced EMF is going to be basically 0, or it's going to be a maximum? No, it's going to be a maximum because the push from the capacitor is a maximum. And so the induced EMF from the inductor is also going to be a maximum. We're just going to follow this line of reasoning right to the end. In subsequent moments, what's going to happen to the magnitude of the inductor's EMF? Decreases rapidly at first, then tapers off. Once again, the current will build to a maximum. Just after the current reaches this maximum, so now it's flowing to the left through this inductor. As soon as it reaches a maximum, it's going to try to taper off, but then at that point, the inductor will say, oh, okay, no, I don't like that change. I'll help you now. Try to buoy you up. What's going to happen then? The inductor's EMF decrease rapidly, then taper off. Nearly done here. When the current next has a value of 0, which plate will be positively charged? Well, now that one's going to be positively charged, and that one's going to be negatively charged. And our part U answer agrees precisely with which lettered part. You can rewind in the video if you wish. Part E. In essence, what's going to happen is round and round we go. Charge sloshing back and forth until it subsides due to friction losses. So what's going to happen in this top part of the circuit, we're going to have current building in the clockwise direction and then tapering off, and then building in the counterclockwise direction and tapering off, and then building in the clockwise back and forth at a particular frequency. And it turns out that the frequency of the sloshing conforms to that equation right there. Whenever we tune a radio to a particular frequency, what are we changing? We are changing the value of that product in that denominator right there. And usually you're doing it by changing the value of the capacitance. But when you tune a radio, that quantity is being changed so that your radio picks up a particular frequency. Almost done. When the maximum charge Q resides on the plates of the capacitor, the total energy of the system can be represented by this equation. We derived this way back when we were young, when we were dealing with capacitors. Then, for any combination of charge on the plates and current through the inductor, because that's what we've been talking about. We've been talking about the capacitor has some charge on it, and then maybe there's some current going through that circuit, and at some point there will be no charge on the capacitor with a maximum current going through the inductor. At some times there will be no current going through the inductor, and the capacitor plates will be charged to a maximum. So the total energy is going to be simply the sum of the charge on the plates at a particular time squared divided by 2c. Usually when we write, often I should say, when we write a lowercase letter, it means that that is a quantity that changes with time. That's what that is. And the energy in the inductor. And energy is conserved. So when the charge on the plates is a maximum, that's the point when there's, at that instant, no current flowing through the circuit. On the other hand, when the current is maximized, there will be no charge on the plates. The plates will be uncharged.